Welcome. We are the SFA ACM chapter. We've been around since 1957, and we serve the software professionals across a wide range of disciplines. We certainly invite any software professional to please either renew your support or to join us. Your participation and financial support really help us in putting on programs, and support for really important programs like the Synopsys Science Fair that we judge every year, and just get to see all this young talent. So thank you very much. And to sign up, please either contact us or look at the newsletter BitDropper, or even go to our website sfaacm.org. Wanted to let you know about a couple of upcoming events. In August, we have one on Monday, the 23rd. It is Secure and Interpretable AI, Scalable, Interactive, and Practical Tools by Dr. Polo Chow, co-director of Georgia Tech's MS Analytics program. He's also an ACM distinguished speaker. In September, we have Embattling for a Deep Fake Dystopia by Dr. Elke Demir, Senior Staff Research Scientist at Intel Corporation, also a ACM distinguished speaker. And for Wednesday, July 21st, 7 p.m., multimodal DL to detect depression and visual. I think that's info for algorithmic thinking. So if you would like to know more about these events, we do put these events up at meetup.com, and the channel is SFA ACM.
Folks, welcome and thank you for joining. As Mike presented, we are really excited to actually have a stellar group of young scientists, innovators. And along with a number of folks who are here from ACM, we're really privileged to vote upon and deliberate upon over, I would say, 600 plus submissions across a variety of categories: biosciences, informatics, all areas of math, physics, chemistry. And from these, in two different segments, basically the lower division and the upper division, we finalized the computer science related awards that SFA ACM has historically supported now for a number of years, right? As part of the Synopsys Science Fair competition. So it is in this vein that we are privileged to have today the first one here, which is on breast cancer. And the speakers for this are Disha and Tanvi. And Disha is a stellar pianist, apparently. I didn't know that when we were voting on this, and has been very actively involved on the community side as well. And of course, is a very proficient coder. And Tanvi, and as you will actually realize, we spoke to all of these really amazing young students when we interviewed them in the preliminary and final rounds. And Tanvi, apart from doing medical science and programming with those interests, apparently also has interest in baking and volunteering and supporting the American Red Cross and raising funds. So she's been awarded the Presidential Service Award, and also does competitive swimming and has made it to the Junior Olympics, Far Western. Disha and Tanvi, off to you guys. And thank you again for being here.
All right, thank you so much. Let me just start our presentation and share my screen. Hello, my name is Disha.
And I'm Tanvi.
So much for the opportunity to present today. We are so excited to showcase our project. It is a tool designed to determine eligibility for the genetic screening of breast cancer, which can lead to early detection and intervention.
This project would not have been possible without our mentors, Dr. Tanu Garg, a geriatric physician, and Dr. Mandeep Singh, a surgical oncologist in India. We would also like to thank our parents for their support and encouragement. And once again, thank you ACM for recognizing our project and giving us this amazing opportunity to present.
On this slide is our agenda for today. First, we will begin with background and context for our project. This section will include information about BRCA mutations and a brief overview of our project. Then we will show video from an expert in this field and give a live demonstration of our website, brcatest.org. Next, we will focus on the design and development of our product. This covers the in-depth process of our logic and programming. The next section is results and impact. It will take you through the testing process of our questionnaire and the impact of this tool. Finally, we will present a future roadmap that highlights our next steps.
Here's the first step, background and context for our project. Let's start with the basics. What is a BRCA gene? It is an abbreviation for breast cancer gene. Everyone has two types of BRCA genes, and they actually help prevent cancer.
However, mutations can occur in the DNA of these tumor-suppressing genes, leading to cancer. These harmful mutations can be detected easily through genetic testing, but are often missed due to a lack of utilization. BRCA mutations are hereditary and can be passed down from generation to generation. If you have a BRCA mutation, you have a 50% chance of passing the mutation to each of your children, making testing even more important.
1 in every 400 people have a BRCA mutation, putting them at greater risk of developing breast cancer, as well as passing the gene down to future generations. Women with harmful mutations in either BRCA1 or BRCA2 genes have risk of breast cancer that is about 5 times the normal risk.
There is a simple blood or saliva test available to determine the existence of a BRCA mutation. Despite the existence of this test since 1996, implementation has been slow for several reasons. Guidelines are very clear on this subject and validated by the CDC and National Cancer Network, but they are complex, scattered, and sometimes redundant. They are difficult to use effectively for primary care physicians during their short patient visits, let alone patients themselves. Even though breast cancer incidence is on the rise all over the world and life-saving treatments are available, this test remains underutilized.
That's where our project comes in. We want to make it easy for patients and primary care physicians to check who is eligible for testing and most likely to benefit. Our project is a simple, intuitive, and intelligent web-based questionnaire powered by a sophisticated and dynamic algorithm that can be administered to patients directly. It asks a minimal amount of questions and lets the users know if they should take a genetic test to determine the existence of a BRCA mutation.
Now let's talk about motivation. The only way to do great work is to love what you do, Steve Jobs. He wrote this because you can give 100% of your time, effort, dedication, and work ethic to an endeavor that you are passionate about. It was devastating when one of our relatives passed away from stage 4 cancer last summer. This experience motivated us to think about how we can make an impact in the field of cancer. We decided to focus on improving access to diagnosis and treatment using modern computing technology available to us. Our goal was to facilitate the use of our technology globally and reach areas where cancer care is not readily available.
Our project aims to combine science and technology to help people. Now we will give you an overview, which includes the process we use to develop our application.
These are the 5 main steps that we use to make our questionnaire. First, we researched the current guidelines determining eligibility for genetic testing. We realized that the guidelines were extremely complex and redundant, so we decided to consolidate them.
We then organized them onto a flowchart in order to make the data more streamlined and comprehensive.
After that, we began to code our algorithm using JavaScript.
Then we sent our questionnaire to multiple doctors to validate its accuracy and functionality.
Once we got the results back, we continuously made changes to our questionnaire until it was 100% accurate, and then moved on to building a website for our application.
Now we will show you a video by our mentor, Dr. Mandeep Singh. He's a surgical oncologist in India and heads the surgery division of Fortis Hospital in Delhi. He sees advanced breast cancer patients daily in his practice and encouraged us to work on this BRCA testing guidelines and access. He hopes that our questionnaire can help thousands of patients get detected early on and seek appropriate treatment. Now we will play the video.
Hello everyone, I'm Dr. Mandeep. I am a senior consultant and I lead my department of head and neck and breast oncology at Fortis Hospital, Vasant Kunj, New Delhi. Today I want to share certain facts around breast cancer. In India, around 170,000 to 200,000 new women are getting breast cancer every year. The average age of presentation for breast cancer in India is lower. It's around 40 to 45 years. In some parts of our country, it is as low as 35 years. A large component of our breast cancer is that triple negative variety, which is an aggressive cancer, and it also has a hereditary predisposition towards breast cancer or even the ovarian cancer. And also the major proportion of our population, when they present for treatment, they are at advanced stages of cancer rather than at the early stages of cancer. Because of these facts, I strongly believe in a dedicated software or a program to ascertain the hereditary component of breast cancer or the hereditary breast ovarian complex, which if we are able to identify before the manifestation of cancer, we can take appropriate preventive steps, or we can help in early detection, which will help in saving precious lives. Thank you.
All right, thank you, Dr. Mandeep, for that informative video. Now we're going to give you a brief demonstration of our website, brcatest.org. Let me just navigate to that page right now. This is the home page with information about the test and forums for discussion. Our goal with these forums was to create a platform to connect patients and specialists. Patients can now ask questions and experts have a channel to answer them. We also created a second forum where users can connect and share their experiences. At the top, this page connects to our questionnaire.
Now we will go through some model situations. A 51-year-old Italian woman goes to her doctor for her physical exam. She has a personal history of breast cancer, which was diagnosed and treated at age 40. She is worried about her risk for further cancers and also for her daughter, who is now 19 years old. Do she and her daughter need genetic testing?
Let's go through that model scenario for the mother first. Her gender is female, and then the next question asks about age. Since it says she's a 51-year-old woman, we will put over 45. The next question is about personal history and asks you to select any of the following cancers you've been diagnosed with. The model situation says she had breast cancer. It says she's an Italian woman, so is not of Ashkenazi Jewish ancestry. And the next question is, what age was her breast cancer diagnosed? It was diagnosed and treated at the age of 40, so prior to 45. Given this, we receive a positive recommendation that she should take the BRCA test based upon the current guidelines. Now let's take the questionnaire again for her 19-year-old daughter. Her daughter is again female and less than 45. However, she has not had any personal history of cancer, so we'll select none. The next question moves on to family history. Here it asks if she has one or more blood relatives with a diagnosis of any of these cancers. And since her mother has had breast cancer, we'll select breast cancer. And given that, you receive another positive recommendation.
Now let's move on to the second case. A 34-year-old Chinese woman had melanoma at the age of 29. However, she has no family history of cancer. She is worried if she might be at risk given her personal history. Does she need any genetic testing? So she is a female. She is 34, which is less than 45. This is a question regarding personal history, and in the description it said that she had a melanoma before. She has no family with any cancers, so we'll click none of the above. And it's also none of the above for this question because this is another one regarding family history. And she has no relatives with any BRCA mutations. So based upon this case, the recommendation is the test is not necessary based upon the current guidelines. So let's head to our third and final case. A 50-year-old male of Indian descent has no personal history of cancer, but has a family history of ovarian cancer. Will he benefit from BRCA testing?
All right, now let's go through this questionnaire for the third and final case. This is a male, and he's of Indian descent and not Ashkenazi Jewish ancestry. So for this question, we'll click no. Then it asks about personal history, and he has no personal history of cancer. So we click none. Then we move on to family history for the male side, and it says, do you have at least one blood relative with any of the following cancers? He's had a family history of ovarian cancer. So we'll select ovarian cancer, and given that, we receive a new recommendation. In some cases, the guidelines are unclear, so we want to make sure users consult professionals to determine the best course of action. If that situation occurs, you receive this recommendation to consult your doctor or meet with a genetic counselor to see if taking the test will be beneficial. All right. Now that we have shown you our final product, let's talk more about the process that led us here. Our first major step was compressing existing guidelines. First, we gathered information from various credible sources, such as the CDC, Mayo Clinic, and NCCN. These guidelines were extremely scattered and complex. Our next step was taking the guidelines from each source and compiling them onto a central list. This way, we had all the information in one place and could begin the next step. Once the list was established, we eliminated repetition and redundancy. We also consolidated multiple questions and concatenated related guidelines. Finally, we translated the complex questions into a readable and comprehensive format. This was the final list, which we used as the basis for our flowchart.
For the flowchart, we began by grouping the questions and organizing them. The basic structure of our flowchart was 1, demographics, 2, personal history, and 3, family history. The next step was to create logic for separate paths. Each question was not applicable to each user, so we created an alternate system. The flowchart became dynamic, which means depending on the user's answer, it will guide them to a corresponding question. This makes the process much more streamlined.
Here is the entire flowchart with all of the connected paths. At the top, we ask about basic demographics, which can be seen in dark blue, and slowly progress towards more complex questions. The area in the light green were added later to improve accuracy, which we'll talk about more as the slideshow progresses.
Now we are going to go into an in-depth coding process.
This slide outlines our steps. First, we created a systematic flow of data. Taking the logic from our flowchart, we began creating a system through code. Our goal was to create a flexible model for our dynamic questions. Second, we started designing the wizard. This involved changing the question displayed correspondingly depending on the user input and translating our logic into an algorithm. Third, we built a website to host our algorithm and provide information regarding BRCA testing and mutations. It can be found at brcatest.org. This user-friendly website was created to host the questionnaire so that it can be accessed by patients around the world, and doctors can use it to screen patients who need genetic testing.
One JavaScript object we used to store our data was an array. They were instrumental in our project since they let us store multiple values in a single variable, which helped keep our code concise. We also utilized indexing as our method of organization. By giving each question an index value, we were able to individually call them, making our code more streamlined and efficient. Within our arrays, we created a format for each section. It included the question, type of question, possible answers, and assigned index. Each component was utilized throughout our code.
Now we will focus on defining the wizard. The first step is to take data from the array. Our function determines the type of question and format. In this snapshot of code, you can see what happens if the question type allows multiple answers. An example of this type of question is the personal history question. The next step is using logic to update the question so it will change depending on the previous answer. To do this, we tapped into our indexing logic. Based on what it a user now chooses, the questionnaire takes them to the corresponding follow-up question. Using this system allowed for flexible code that was built on an efficient model. Then, according to the user's answer, we took them to a different index value for their next question until they received their recommendation. This created a modular design that was both effective and accurate. Once we had created the backbone of our questionnaire, we began enhancing the code.
After that comes embedding the newly displayed question onto our website. To enhance our application, we also programmed a back button. Using alerts, we were able to eliminate invalid responses from users. We embedded a restraint in our JavaScript code that alerted the browser when two contrasting options were selected. If patients entered a history of cancer, but also chose a contradicting option, our algorithm prevents the questionnaire from resuming until the response is corrected. This function helps make the questionnaire more logical and accurate, while still keeping the process concise. This snapshot of code displays what happens when a user selects both no cancer and a cancer. Now we will go into a step-by-step explanation of our website structure and design.
Here is a basic outline of our process, gathering information. We researched the key components of creating a website and determined our plan.
Then, for design, we created the basic layout and chose our theme.
After that, we programmed the web pages through JavaScript and HTML and embedded the questionnaire onto our site. We also added more advanced features like forums for patients and experts.
Next, we began our testing phase. This included testing website speed, multiple screens compatibility, and cross-browser compatibility.
Finally, maintenance. To continuously improve our website, we make adjustments on a monthly basis.
Gathering information. To gather useful information, we first needed to have a clear understanding of our target audience as well as our primary goal. Our goal was to seamlessly integrate our questionnaire onto an informative website which could provide additional functionality. As for the target audience, ours was doctors and patients above the age of 18.
Design. We wanted to identify how to make our website as well as the scope. For the languages, we chose HTML and JavaScript, standard web development options. To enhance our graphics and functionality, we imported Bootstrap libraries. Identifying the scope was the process of deciding what additional features we wanted. Some of these components included, number one, forums for discussion between patients and specialists, two, informative medical sources, and three, easy navigation.
On this slide is a sitemap. We created it to help determine the layout and structure of our website. The home page connects to several other pages. It directly links to our questionnaire, the team page, our mission page, and forums. Then the forum page leads to two different types, one for doctors and one for patients.
And now, trials and results. We prepared a mock list of 30 patient scenarios, which were approved by doctors beforehand. After testing them on our model, physicians validated our results, and we made adjustments according to the feedback. This process was repeated several times.
The success rate for trial 1 was 83%. 25 out of 30 of our patient scenarios received an accurate result. The main root of the problem was a bias towards positive results. Some of the patients who should have received negative results actually received positive results. This was a problem because people who don't need the BRCA test shouldn't receive a false recommendation because it may cause them to have stress or anxiety, and gene tests are also very expensive.
To fix this issue, we revisited our logic tree and reorganized questions depending on importance. Certain questions, such as personal history, had to be prioritized before family history. We also received feedback from professionals that we were asking about ancestry too early in the process, so we adjusted our logic in the back end. These changes led to 94% accuracy.
Finally, we tested a third time. To bring our accuracy up, we added 3 additional questions. These questions added more detail and elaborated further. When we got the results back, there was a balance of positive and negative results from the questionnaire, which pleased us. The questions we added were highlighted in light green in the flowchart, as shown before. The third test received 100% accuracy. And finally, the impact and magnitude of the project.
This questionnaire is accessible to patients and doctors all over the globe. Traditionally, people had to decipher complex guidelines from various sources, which were difficult for even specialists to understand. Now, thanks to this tool, it only takes a few minutes to get an accurate recommendation. In addition, it takes away the human error factor. This modular algorithm will not move forward unless the questions are answered. This eliminates the chances of forgetting a question or missing a part of medical history.
In many developing countries, there is a lack of information and resources available about BRCA testing. By first launching our questionnaire in India and Afghanistan, and then later expanding globally, we hope to create a powerful tool which can help both doctors and patients. In addition, our website provides a channel of information and forums for communication.
Studies show that early intervention surgeries for patients found BRCA positive can improve survival rates by 20% or more. If our questionnaire is launched throughout the world, we can increase early intervention significantly. With this questionnaire, genetic testing for breast cancer can be made available to people who need it. It can help increase both awareness and application. Doctors who were previously unaware and unable to use these guidelines effectively can now give their patients this tool. If more eligible candidates get tested, it will lead to early detection and intervention, which can save countless lives.
Here is our future roadmap, which outlines our next steps. First, we want to make our website multilingual so it can be launched globally. Another goal is to connect with genetic counselors. Once users receive a recommendation, we want to help them determine their next steps and refer them to labs if needed. This facilitates a comprehensive experience where we can guide users through the process. Third, we will develop an app on iOS and Android to improve accessibility on mobile devices. Finally, we would like to expand our tool to cover other BRCA-associated cancers. This will increase the impact of our project and help us expand further.
Thank you so much for this amazing opportunity to present. We really enjoyed showing ACM our project and are ready to answer any questions. Thank you.
Okay, thank you, Disha and Tanvi. Very, very, very exciting. I'll actually start off with one question, and just the reason for this questionnaire now is so we can, keep the flow going before we move to the second topic. So I hope it's okay with everyone. All right. So I'll actually start off with one question. So can you tell us a little bit about what your starting point was for determining this decision tree that you had developed? Was it based on, you mentioned that the inputs were actually pretty complicated. Doctors have a hard time going through this, let alone patients. So what did you guys start with to actually streamline this into a series of, say, 10 to 15 questions that allow you to zoom in, right, very accurately into whether testing should be done or not? What guidelines did you start with?
All right, I can actually share my screen and show you a few examples of some of the guidelines. We took them from various sources, and I can show you one of the major examples. Let me just pull it up really quickly. And in the meanwhile, Tanvi, you can talk a little bit about the guidelines.
So our sources for the guidelines include the CDC website, Mayo Clinic guidelines, and NCCN, which is the National Comprehensive Cancer Network. So they were all reliable sources that doctors verified. Got
it. And just a quick follow-up, did you find any conflicting recommendations during these guidelines that you were implementing?
Yeah, so actually I can answer that. So this is an example. This is from Mayo Clinic. These are some of their guidelines. And so some guidelines like this, we had to break them down and then we had to compare them with other websites which had similar types of guidelines. and see which ones were the most accurate. And to do that, we looked at the most verified sources. And since these sources were so verified, most of them matched up. But when they didn't, we consulted experts in the field and made sure that it was medically accurate.
Fantastic, thank you. Any questions from folks on the call?
If there are no questions, I have one that's related to this project. Did it help steer you in a direction of pursuing medicine or computer science?
You can start.
So it actually did. I can speak for myself. Because of this project, we started it because one of our relatives passed away from stage 4 cancer. So this project actually grew my interest in the cancer field. So I'm more eager to learn about it. So I'm hoping to go into the medical field of oncology, and Disha can talk about what she wants to do.
So my passions have always been technology and medicine, actually. So this project was a great way to combine both of them and really use technology to make an impact in that field. And now that we've started, it's definitely very motivating and we can do many more things. So it's a great starting point and platform to continue doing that. Are there any more questions?
If people are shy, they can also put it into the chat.
Yeah, this is really, really a wonderful, I think, service to the community. And are you guys going to try to make this into a mobile app or anything?
Yeah, that's on our future roadmap. And we're also hoping to build upon this. And like we said, go into other BRCA associated cancers. And then once we do that, we hope to kind of enhance our coding and maybe bring machine learning and AI into it, just to make it even more comprehensive. So that's definitely what we hope to do.
From a programmatic point of view, I mean, there is kind of two different styles of programming. If you guys are not familiar, that's okay, but declarative and imperative programming. And this particular, use case really kind of falls into sort of, imperative programming style. It's really hard to code these things up, a bunch of if-else statements. And then if I were to kind of think of this in a very naive kind of way, right, I would have a series of if-else statements and then just keep going down this path. Did you guys have any programming ahas that allowed you to, kind of get to the end goal while still, keeping the overall structure more flexible in case, a new research came out and that said, hey, you should consider this new factor, more favorably, right, towards the final analysis.
Yeah. Yeah. Oh, sorry. Continue.
Go ahead.
So I can talk about this. So actually, that's what we did. We started with Python because as being 7th graders, Python was more familiar to us, and that's what we felt comfortable with. So Python worked extremely well for us at the beginning of the process. However, as our questionnaire started developing, we realized that Python wasn't fitting our needs. Once we reached this crossroad, we had two options. We could either continue with Python and forcibly embed it onto a website or reprogram our code in JavaScript. And although the second option was more difficult, it would be a lot more efficient for us. So we cleaned up the code and made the model more flexible and dynamic. And that ended up benefiting us a lot in the long run.
Okay,
yeah.
Cool.
And just to add to that, we actually did start with just a series of if-else statements, but then once we made the transition into JavaScript, which kind of just made our code more complex and efficient, we did try to create a flexible model with functions, which would probably make it easier to adjust, and it was just a lot shorter and more concise. So,
fantastic. Yeah, good to hear. All right, folks, I think we are up at time. Thank you again, everyone. Virtual claps for this beautiful presentation, and good luck in your future endeavors in every sense of the word. Okay.
Thank you.
Thank you.
You bet. You bet. Any other questions going once and twice? Okay. All right. Okay, so our second topic for the day is cardiovascular disease diagnosis, and our three speakers for this are Milind, Christopher, and Jay. Milind is a professional chess player, who's attained the title of National Masters in Chess with a peak chess rating of 2211, which means he can handily beat me with one hand behind his back. He has placed first in the California State Championships, National Junior Championships, fourth, and has represented the USA twice in World Youth Chess Championships. Fantastic, Milind. Great to have you here. Christopher is conducting a literature research on stingless bees of Central America with Professor Chaplin of the Woods Institute of the Environment. And his hobbies are solving Rubik's Cubes and chess puzzles. Fantastic. Christopher, he's also an avid pianist and has recently debuted at Carnegie Hall and has won numerous competitions. And at this young age, he's also enrolled in De Anza College. Fantastic, Christopher. Welcome, welcome. And finally, we have Jai, who's done mathematical research at the Euclid Lab, where he's already published a research paper on the Collat's conjecture, an unsolved math problem. And he teaches math competition preparation to elementary and middle school students. And he's also an author of Conquering the AMC-8, a 242-page AMC-8 prep book. And he's a teacher of machine learning, having given lectures at STEM Boost. All three of you, a very warm welcome. Please go ahead and take it over on cardiovascular disease diagnosis.
Thank you so much for the introduction. Could I share my screen?
Yes.
Okay, thank you.
Hello, everyone. My name is Christopher.
My name is Jay.
And my name is Milind.
And we thank you so much for coming to the seminar tonight, despite all your busy schedules. And we are extremely glad to have you here. And we also want to extend our deepest thanks to ACM for giving us this opportunity to showcase our work to the community. And that said, we are excited to now present our research on cardiovascular disease diagnosis using deep neural networks.
Cardiovascular disease causes 25% of deaths in America, making it the leading cause of death. Misdiagnosis is a huge part of this issue, as it causes upwards of 11,000 annual deaths. The goal of this project was not only to increase the accuracy, but also the availability of cardiovascular disease diagnosis. To do this, specifically, we wanted to use deep learning to diagnose cardiovascular disease with 70 to 75% binary accuracy. To do this, we used a data set of 11 features, very high-level features that can be attained at any clinic in any rural area or third world country, in addition to a data set of 70,000 people.
In order to understand more about our data set, we first use exploratory data analysis to figure out each feature's contribution to one's increased risk of contracting heart disease. As you can see on the chart on the right, the larger that the circle is, the more that it impacts one's increased risk of contracting heart disease. For example, cholesterol and blood pressure have relatively large circles, and thus they have a big impact on one's chance of contracting heart disease. And we used a technique called exploratory data analysis to figure this out. Then, in order to visualize our data, we projected the 11-dimensional data because we were given 11 features and projected this down onto a 2-dimensional plane, which allowed us to visualize data and graph it using a technique called principal component analysis. After graphing this data, we noticed distinct clumps in the data, and we noticed that the data was clumped into separate clusters. And so we were inspired to use k-means clustering to cluster the data in order to segment the data into different groups. And then we also had an hypothesis that the different groups of unhealthy patients, each of them would have a separate type of cardiovascular disease. And so we hypothesized this, and we analyzed the centroids of each cluster in order to try and figure out what these specific diseases were. After this, we used several different types of machine learning models in order to actually predict whether a patient, given some 11 features, would actually contract heart disease. And these 4 different types of machine learning models was logistic regression, random forest, extreme gradient boosting, and support vector machines. After using these machine learning models and training them, we used them as a standard of comparison for our later deep learning models, which included the shallow neural network first. Then we deepened the neural network with a deep neural network. Then we implemented some advanced techniques for a deep neural network. And finally, we implemented it using Keras, whereas the previous three were implemented from scratch using NumPy.
The performance of our final model, the Keras implementation, had a binary accuracy of 74.2% and an F1 score of 0.73. We believe that our project has applications in medical diagnosis, forecasting medical equipment in hospitals, and providing detailed, personalized statistics to make people more aware about how they treat and how they view their physical health. We also believe that our project is versatile and can be applied to rural areas and third world countries. So because of the high level features that that our model takes in as inputs, these features can be collected at any local clinic in rural areas and third world countries. And so we believe it is versatile in that way.
Now I would like to get into the bulk of our research, starting with the introduction and by going over some of the current methods for diagnosis that doctors use to diagnose patients with cardiovascular disease the traditional way. Now listed here are some of the most common procedures used by doctors. For example, the electrocardiogram can allow doctors to detect some abnormalities in the heart. The cardiac MRI can generate some very high quality 3D images of the chest area, and some tests for amino acids such as homocysteine, which is a very essential biomarker of the disease, as well as lipid profiles can be conducted to give doctors a better sense of patients' medical conditions. But the area of research that we wanted to improve with our project was surrounding automated diagnosis. So I briefly want to address some of the ongoing research in this field, starting with models that are trained on the Cleveland database. Now, the Cleveland database is a data set that consists of 303 patients and 75 features, meaning even though there is a little number of patients, there's a large number of data for each of these patients. And because there are only a little number of patients in the data set, scientists and researchers have built models that have achieved 85 to 90% on the Cleveland database. Now, another focus area of research for automated diagnosis is by building models on synthesized patient data. And while we cannot yet project the effectiveness of this approach to modeling the real patient trends that we observe in society, we know that because of the abundance of data, more accurate models are able to be trained. Now I want to get into the data set that we specifically chose for our project. We selected a publicly available data set from Kaggle that consisted of 11 objective, examination, and subjective features. The objective features were simple numerical features such as age, height, weight, and gender. And of the examination features, which are features that can be obtained from any medical clinic, like Jay said, even in third world countries and rural locations, these examination features are blood pressure, cholesterol, and glucose, where cholesterol and glucose are given on a scale of 1, 2, and 3, with 1 corresponding to normal, 2 corresponding to above normal, and 3 corresponding to well above normal. And finally, our data set did include 3 subjective features, meaning these features were simply answers to yes or no questions by the patients, such as whether they smoked, whether they drink alcohol, and whether they have some sort of physical activity in their lifestyles. And we used all 11 features to predict the target label, which was whether or not a given patient has cardiovascular disease.
In order to track our progress as we went along with this research project, we first had to determine a project goal. In order to do this, we had an expert manually classify a random sample of 100 patients in the data set, and this expert achieved a binary accuracy of 77% and an F1 score of 0.77. We then regarded this classification performance as a proxy for Bayes accuracy, which is the highest theoretical accuracy, and after adjusting the numbers a little bit, we determined our project goal to be for our most advanced model to achieve a binary accuracy of around 70 to 75%, and an F1 score of 0.7 to 0.75.
Now, before we go on to the exploratory data analysis part of our project, we wanted to remove any outliers in our data set that could have been wrongly inputted when creating the data set. So first, what we did is for each feature, we calculated the interquartile range. So let's take blood pressure, for example. What we do is we calculate the IQR, or the interquartile range, as quartile 3 minus quartile 1. And so essentially this is the 75th percentile of blood pressure minus the 25th percentile of blood pressure. And then we can define an upper threshold as quartile 3 plus 2 times the IQR, and the lower threshold as quartile 1 minus 2 times the IQR. Essentially, any person in the data set who has blood pressure lower than the lower threshold or above the upper threshold is removed because they are considered an outlier. And we took this method from the 1.5 times IQR rule used in statistics. So usually in statistics, there would be a 1.5 here instead of 2. But after examining the our data set more thoroughly, we found that 2 was a more accurate representation. Using 2 was a more accurate representation of the outliers that were in our data set. And therefore, this is how we decided to remove all of the outliers. Now, after we removed these outliers, we decided to go on to the exploratory data analysis. And the whole idea behind this is to find out what is the effect of each feature on cardiovascular disease, and how important is it in diagnosing the disease. So let's take the example of males. So what is the increased chance of being a male on one's chances of contracting heart disease? So how does that feature affect? So what we do is we calculate X as the number of males who have cardiovascular disease, or the number of males who have cardiovascular disease over the total number of males. And this is actually the percentage of males who have cardiovascular disease. And Y is the number of females who have cardiovascular disease over the total number of females. And this is the percentage of females who have cardiovascular disease. And to calculate the effect of being male on one's chances of contracting heart disease, we simply did X minus Y. So we did this similarly for all of the discrete features. So gender is a discrete feature, and other features like inactivity or activity and inactivity, that's also a discrete feature, and so on. And so we did this for each of the discrete features. Now what happened was we ran into a problem when we went to continuous features. So continuous features actually don't have separate classes that they're placed in. So again, let's take blood pressure as the example. Here, what we did is, to combat this issue, we made 2 artificial classes of blood pressure. So anybody who has a blood pressure higher than the median blood pressure is put into a sort of upper class. And anybody who has blood pressure lower than the median blood pressure is put into a sort of lower class. And essentially in this way, we are able to treat this discrete feature, which was blood pressure, which can take on an infinite range of values, as simply a discrete feature, which takes on only 2 values. And so in this way, we were able to treat this feature as the discrete feature and therefore do the same exploratory data analysis as we had done before. And so we did this for each of the continuous features, including height and weight and age, and so on.
In order to visualize our data set, we use principal component analysis to project the 11-dimensional data onto a 2-dimensional plane, which would allow us to visualize it. While doing this process, 70.66% of the variance was maintained. When you project an 11-dimensional data, and if you compress it down to a 2-dimensional plane, some of the information that is present within the 11-dimensional data is lost because you're reducing the amount of dimensions. And when we say 70.66% of the variance is maintained, we mean that around 70% of the information contained in the data is still maintained. Now you can see on the top left, this is a real diagram from when we used PCA to visualize our data. And as you can see here, the data looks like it's clustered into around 4 different groups. So after noticing these clumps of data, we were inspired to use k-means clustering to cluster the patients into 8 different groups. And we used the ELBA method to determine the exact number of clusters. And as you can see on the graph on the top right, which is actually also from our actual data, the elbow of the graph looks like it's around 8 clusters. So we decided to use 8 clusters to cluster the patients. And our hypothesis was that patients in different clusters would have different diseases. So for example, patients in cluster 1 would suffer from a separate disease than patients in cluster 2. And as you can see on the graph on the bottom, we clustered only the unhealthy patients, and we plotted them on this graph. And we hope to analyze the centroids in order to try to predict which cluster corresponds to which disease.
Now, after we removed the outliers from our data set, and after we got a better sense of the data set by visualizing it, we then turned to our machine learning models, which would act as our standards of comparison for the deep learning models implemented in the future. The 4 machine learning models we used were logistic regression, random forest, extreme gradient boosting, and support vector machines. But we also needed a way to assess the accuracy of our models. So we used 2 main performance metrics. The first being the binary accuracy, which is simply the number of correct predictions by the model divided by the total examples and expressed as a percentage. The F1 score was also another performance metrics that we used when assessing our models. And we used the F1 score because it disincentivizes random predictions by using the concepts of precision and recall.
After doing the machine learning models, training the machine learning models, we moved on to the deep learning models. And to be specific, the machine learning models were to act as a standard of comparison for our deep learning models. And essentially, we wanted to create the final deep learning models so that they beat the performance of the machine learning models we had trained prior to that. So our first deep learning model was a quick implementation using NumPy. And this consisted of the input layer, which fed into a dense hidden layer of 8 hidden nodes, and then to 1 binary label output. This was built using Scratch in NumPy, and it was a very shallow neural network. And so we did not apply any advanced techniques here. And this was batch gradient descent. And the model was training really, really slowly for this model. So even after 100,000 iterations of training, we were not able to get as low of a cost as we had hoped. So we decided, instead of waiting for hundreds of thousands of iterations and many, many hours of training, to just look for a better model architecture. So we added more hidden layers in the next model.
As Jay had mentioned just previously, the shallow neural network wasn't doing well, and so we decided to add 5 more hidden layers, each with 8 hidden units, to make the neural network a deep neural network with 6 hidden layers and 8 hidden units in each layer. However, even with such a more lengthened neural network, the neural network was still training very slowly, and it wasn't converging even after a very large amount of iterations, such as around 100,000 iterations. And thus, in order to decrease train times and speed up the training, we decided to use advanced techniques and different optimization techniques in our next iteration of the model.
Like Milind said, the second neural network that we built failed to converge optimally even after a large number of iterations. So we turned to our 3rd generation neural network, and this network had the same architecture as the previous one, still with 6 hidden layers and 8 nodes per hidden layer. But for this network, we use some techniques such as HE's initialization and atom optimization. And on the next slide, Jay will specifically talk about how these techniques, as well as some other more advanced techniques that we implemented, affect the learning and the accuracy of the model.
We implemented our final model using the Keras library. So while the last three models were built from scratch using NumPy, this one was built using the Keras library. So over here, you can see that we have the same number of hidden layers, except now our model is much, much bigger because it has 128 hidden nodes per layer. And essentially, we use some advanced techniques, two of which are common to the last generation, which are atom optimization and HE's initialization. So these two were also used in the third generation model, but we also used a couple more advanced techniques, which I'll talk about now. So atom optimization, mini batch gradient descent, and batch normalization were all used to speed up the long train times that we had encountered in the first two deep learning models. So to avoid the hundreds of thousands of iterations of training, these are the advanced techniques that we used. In addition to this, we used HE's initialization, and this partially helped with the long train times because of the initialization of parameters, but mainly it was used to combat the problem of vanishing and exploding gradients. So in addition to this, we used early stopping, and we will show you some graphs about the learning curves for these models. And for this model specifically, you'll see on the x-axis there will be the number of iterations, and on the y-axis there is the cost. And so over the number of iterations, the cost should be decreasing. And at the end, when the model has learned, the cost should sort of flatten out at the end. But for us, for this specific model, it will look like the curve has not completely flattened yet, but we assure you this is just because we used early stopping. And essentially what early stopping is that we stop training our model right when the cost on the validation set, or the set that we actually want to do well on, is starts to go up. So this indicates when the model has been overfit to the train set in comparison to the test set. And finally, we used dropout regularization. And dropout regularization was another factor that we used just to combat overfitting on our train set in comparison to the validation set, which is actually what we wanted to do well on for the final model performance.
In the graph on the left, we have plotted the increased risk of heart disease against each feature, and this was from the results of our exploratory data analysis. As you can see, features such as blood pressure have a high increased risk of one's contracting heart disease, around 30%, and same with high cholesterol, which has around which gives you an extra 33% chance of contracting heart disease, whereas something such as being male or having a shorter height only gives you around a 1% chance of increased risk of heart disease, which is statistically insignificant. One thing about the graph that we thought was surprising was that inactivity only corresponded to a 5% increased risk of heart disease, which we thought was very surprising because we thought inactivity would play a larger role since exercise has been long touted to be a preventer of heart disease. However, this could also be due to the fact that inactivity was subjective features, and thus patients may have unknowingly misclassified themselves, and thus inactivity is not as big of a factor as we might expect it to be. And the same data, we have replotted it in a different way on the right side as a function of the diameter of the circle. And here you can see the larger the circle, the more impactful the feature is on your increased risk of heart disease. So for example, cholesterol and blood pressure have a big impact since they have bigger circles, whereas something such as glucose and weight have a smaller impact, and thus they are plotted with smaller circles.
Recall that after our EDA, we compressed the dimensions of our data so we could visualize it, and this inspired the clustering of the data. So now I want to share the results of our clustering and present the centroid data. We can see that we clustered the data into 8 clusters, each with a different number of patients. And I want to note that clusters 4 and 6 are especially large, containing more than 12,000 patients each. And we can also see the average age of each cluster, the average gender, height, weight of each cluster, and the average measurements for each of the features for each of the clusters. And we were able to use the horizontal rows of this table, which are the centroids, to deduce some of the more specific types of diseases that patients might have in each cluster. This allowed us to dive beyond the binary labels in the dataset and make some more specific inferences. For example, for cluster 1, we hypothesized that patients suffer from an early stage of heart disease, while cluster 2 represents patients who have a more complicated condition of liver cirrhosis. And we did this for all 8 clusters, and I will share our thought process a few slides later.
So here are the results for the machine learning models. Okay, so we have trained the logistic regression model, the support vector machine, the extreme gradient boosting, random forest, and here we have the shallow neural network just for reference. This is not a machine learning model, but this is here just for reference. And out of all of these machine learning models, you can see that support vector machine actually had the best performance with a binary accuracy of 73% and an F1 score of 0.71. And thus, we decided to use this performance from the support vector machine as the standard of comparison for our deep learning models. So we wanted our final deep learning models to have a better performance than the support vector machine did. Before Milind shows the performance for each of the deep learning models, I want to show you some learning curves. And here, for each of the models, you can see the number of iterations that the deep learning model was trained versus the cost of that model. And here, for the shallow neural network, you can see that over 100,000 iterations, the cost seems to be decreasing and there seems to be learning still going on. But even after 100,000 iterations, as you can see on the y-axis, the cost has not decreased a sufficient amount. And we did not want to wait for hundreds of thousands of iterations of training to train this model. Rather, we wanted to look for a better model by adding more layers or implementing some advanced techniques that we could decrease the train time for this model. And so just to be specific, this 100,000 iterations took hours upon hours of training. So that's why we wanted to decrease the time. So we next we implemented the deep neural network. And this was significantly better in terms of the cost. But you can see that after 10,000 to 20,000 iterations of training, there's not much learning going on, though there is a general downward trend. Most of this is just noise and not much learning. So, and again, there was 100,000 iterations of training, which is many iterations and a lot of time to train the models. So to avoid the long train times and basically to improve the cost of this model, we decided to implement advanced techniques such as atom optimization and HE's initialization in the third model, the optimized deep neural network. So here we implement, so this was our motivation to implement atom optimization and HE's initialization. So you can see that actually after only 500 iterations of training, we were able to bring our model down to a cost that was lower than the previous 2 models were. And so this was significantly better in terms of their performance overall, as well as the cost. But we decided to go even a step further to implement even more advanced techniques using the Keras library. So I said before that we used more advanced techniques, and I mentioned those on a previous slide. But we also did implement atom optimization and HE's initialization, along with, I'll mention one other one, which was early stopping. So you can see that this doesn't completely flatten out at the end, but we assure you that is because we did stop training after the cost on the validation set started to increase and we started to overfit our train set. And you can see over here that within less than 160 iterations, the cost was able to achieve, or this model was able to achieve a lower cost than all of the other models. And so this model was not only able to fulfill our project goal that we had set in the beginning, but also to beat the support vector machine, which was our standard of comparison machine learning model?
So from the results of our deep learning models, both of our advanced neural networks were able to perform better than their standard of comparison, which was the support vector machines. Firstly, the shallow neural network did the worst, achieving only a binary accuracy of 64% and an F1 score of 0.62. The next best was the deep neural network, which achieved a binary accuracy of around 70% and an F1 score of 0.72, so almost getting our project goal. But both our deep neural network with advanced techniques and the Keras implementation of our neural network were able to achieve binary accuracies of around 73 to 74% and F1 scores of around 0.73, and thus they were able to achieve our project goal. Now, comparing this to the performance of machine learning and or deep learning models utilized by researchers, Robert and others were able to use a logistic regression algorithm for heart disease detection and achieve a 77% accuracy. Wingcade and others were able to use a multilayer perceptron classifier or deep neural network for heart disease diagnosis and achieve an accuracy of 80%. And Leocott and others were able to use a stacked support vector machine for the prediction of a heart disease, and they achieved an accuracy of around 91%, although they only used selected features for their support vector machines. However, it's important to remember that all three of these researchers conducted the research on the Cleveland dataset, which gives 75 detailed features for each patient, whereas the dataset that we used only gives 11 very high levels of features that Christopher had explained previously. And thus our algorithm had a lot less features per patient to go off of, and thus may have had a harder time learning as many complex trends because it wasn't given as much data as the Cleveland dataset provided. However, it did give many more patients, which is why we decided to choose this dataset over the Cleveland dataset.
Now I want to dive into the thought process behind the clustering portion of our research. And first I want to mention that all clusters of patients did have an objectively high BMI and blood pressure, but I will still be using the terms slightly lower and slightly higher to address these features, but just understand that these are going to be on a relative scale. And we also did combine clusters for which we thought patients had similar medical characteristics going off the centroids. So first, I want to start with clusters 1, 5, and 7, which we did indeed combine. And we can see that patients in these three clusters have an average BMI of 27 and also a slightly higher blood pressure, indicating that they're borderline hypertension patients. But all patients in these three clusters have a cholesterol and glucose level that are normal. And this led us to think that while all patients do have cardiovascular disease, it must be at an early stage, which is why we identified patients having an early stage of heart disease. However, 100% of patients in cluster 7 are inactive, which is why we hypothesized cluster 7 to represent patients who have edema, which is a condition that is the direct result of being inactive that involves watery fluid building up in the cavity of the body. And moving on to cluster 2, we see that patients have a slightly higher BMI as well as a slightly higher blood pressure. But the most important feature of this cluster was that all patients drink alcohol and all patients have higher than normal cholesterol and glucose levels. We think that these two adverse features are interrelated, and we also think that because of patients' unhealthy alcohol drinking problems, they suffer from pre-existing liver conditions such as cirrhosis, which is known to adversely affect the progression of heart failure. As for clusters 3 and 6, which we again combined, we recognize that although patients had a BMI of 28, which was slightly lower than the group we just previously analyzed, all patients had very unhealthy habits of smoking and drinking alcohol. And because of these unhealthy habits, we were led to believe that patients have atherosclerosis, which is basically the buildup of plaque in their blood vessels. And we think that atherosclerosis is a main driving factor in the deterioration of their liver and progression of their heart disease. And moving on to cluster 4, we thought that this was one of the most intriguing clusters because right off the bat, we recognized that patients had a well above normal cholesterol and glucose levels, which definitely indicates the possibility of atherosclerosis. But we also saw that patients have a very high BMI of 29, as well as a high blood pressure. But the most compelling factor in this cluster was that there were more than 16,000 patients. And out of the near 35,000 patients we clustered, 16,000 is a large proportion. And this led us to believe that cluster 4 represents patients who suffer from diabetes, especially because the disease of diabetes is so prevalent in our society in the modern day. And in addition to diabetes, we hypothesized that patients have dyslipidemia because the proportion of their lipids is so out of balance. Now, finally, we get to cluster 8, in which patients do have a high BMI of 29, as well as a very high cholesterol level. But other than that, all features of the patients are relatively healthy, which is why we hypothesized cluster 8 represents patients who suffer from an early stage of heart failure, but their hypercholesterolemia does pose a threat that looms in the future.
To reiterate, our final model was able to achieve a binary accuracy of 74.2% compared to our goal, which was to achieve a binary accuracy of 70 to 75%. We were able to achieve an F1 score of 0.73 with our final model, and our goal was to achieve a binary F1 score of 0.7 to 0.75. So both the targets for our binary accuracy and F1 score were met. Now, comparing the performance of our final model to performance of other models on different data sets, our data set contains 70,000 examples and each with 11 features. And we used a 6-layer neural network with 128 hidden units each to achieve a binary accuracy of 74.2%. Now, on a synthesized data set where algorithms use real-world examples to create synthesized data that reflects real-world trends, this data set contained 3 million examples that were synthesized using these algorithms. And each of these examples had around 130 features synthesized. And when models were trained on this synthesized data set using a 30-layer and each layer with 1,024 hidden units, the model was able to achieve a binary accuracy of around 90.3%. And now comparing this to the Cleveland data set, where there are only 300 examples, but these are real patients, and 75 features are given for each patient, although not all features are provided for each patient. Researchers were able to achieve an accuracy of around 91.1% using multiple different models. Now, one of the reasons that our accuracy could be lower than the accuracies for the other data sets was that our goal in this project was to try to use very high level, very simple features for heart disease diagnosis, because we wanted this to work in third world countries and rural applications. And so our data set only contained 11 features compared to the synthesized data set, which has 130 features for each patient, and the Cleveland data set, which has 75 features for each patient. And so our algorithm did not have as much data to train off of, and our neural network thus did not have as much detailed, comprehensive data on each patient. Another reason that our model may not have done as well as it could have is that large neural networks tend to perform better when given a lot of data, and with the more data they're given, the better they do. Comparing this to small neural networks, which do better when there's only a small amount of data, and traditional machine learning, which does well only when there's a very, 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 very tiny amount of data, it's possible that our final model did not have as much data as it needed, as it only had 70,000 examples compared to the nearly 3 million examples in the synthesized data set. And thus, perhaps if we had more examples, it could be possible that our neural network would be doing even better, since it's already such a big and robust neural network. Now, when embarking on this research project, we ran into many different problems. Some of the most noteworthy was that we had a very difficult time in finding the correct value of the learning rate. And so some different approaches we tried to help solve this problem was learning rate decay, where the learning rate progressively becomes smaller and smaller as the number of iterations becomes more and more. Atom optimization, which progressively tunes the learning rate according to exponentially weighted moving averages of the gradients. There was hyperparameter tuning, where we tune the learning rate using different models and running many different models to see which type of learning rate would fit the best. We had implementation bugs regarding the indexing of elements when we were trying to implement our neural network, which we solved by checking each part of the neural network and checking using print statements to look at where we were going wrong. There were a few bugs in backpropagation, which we resolved by using gradient checking, which is where you compute the gradients or derivatives with respect to the weights and you compute this numerically as opposed to using backpropagation. And then we can compare the gradients computed using backpropagation and using gradient checking in order to check that our gradients that we computed using backpropagation were correct. Then there may have been human error in the data set, which we resolved using the statistical removal of outliers, like Jay had explained earlier. And finally, there are the long train times, which we improved by using techniques such as atom optimization and batch normalization. In the future, we hope to utilize different types of architecture, such as convolutional neural networks, to make our models more robust. We hope to train bigger models with more hidden units and more hidden layers to hopefully give us a better chance at improving our accuracy. We hope to implement more techniques such as L2 regularization to decrease variance and combat overfitting. And finally, we also hope to use transfer learning from neural networks that have been trained with much more data, such as the neural network that has been trained on the synthesized data set. We hope to use some of these weights and freeze them in the first few layers. And thus, this will give our neural network as a boost because the synthesized data set neural network has been trained on so many more patients. And thus, it could really help us for our applications because our data set only contains 70,000 examples. And by using transfer learning from a neural network that has been trained on so many more examples, it could really help the accuracy and give a boost to the neural network, which would really help the performance.
We believe that our project has many applications, including the most obvious yet the most important, which is improving patient diagnosis. We can collect the easily accessible features that are available in even rural areas and third world countries to diagnose high-risk patients with cardiovascular disease and give them the proper medical treatment that they need. In addition to this, this very important and significant application, we can also do some other applications which are personalized statistics, so giving personalized statistics to people to make them more aware about how they treat their physical health and how they view their physical health. So for example, we can say, if you lose 8 pounds, you could lower your risk for cardiovascular disease by 15%. Or we can charge personalized life and health insurance rates. So by determining one's risk for heart disease, we can actually charge a personalized life and health insurance rate. In addition to this, we can, instead of taking individuals as inputs, we can take in the inputs of whole cities and whole towns and the medical information from entire hospitals, and use our model to forecast the demand of medical equipment in these hospitals and help cities, towns, and hospitals budget their money. Finally, we can create a tangible product a tangible product that uses deep learning to help patients diagnose cardiovascular disease from the convenience of a mobile app in the comfort of their own homes. Thank you so much for listening to our presentation. We hope you learned a lot about cardiovascular disease diagnosis, and we were really excited to share this project with you. If anybody is interested in this kind of research where we use cardiovascular disease diagnosis or similar projects where we use predictive models for real-world applications, please let us know so that we can contact you after the presentation is over. And now, thank you again so much. If anybody has any questions, we can take those now.
Excellent work, Jai, Milind, and Christopher. Very good presentation and very well presented series of results. As I had questions, you kept on answering those mental questions that I had. So I think you did a really good job there. I'll kick us off here with one question, and any one of you can probably take it. So one of the dangers of developing a very wide and maybe even a very deep model is that you can overfit on the data that you're training on. Can you tell me whether you used test data and whether you kept it isolated from the training, and how did that process go?
So yeah, so we did use validation data, and I think actually like all of the figures that we presented to you, so 74% binary accuracy for our final model, and I believe around 0.73 F1 score. That was actually all on the validation set. So it was not on the train set. And I think in the to avoid the overfitting, as you were saying, we foresaw that problem. And for the final model, the Keras implementation, we also implemented dropout regularization and early stopping to prevent that overfitting from happening. And yeah, I think, does that answer your question?
So just to be sure, when you use test data, so validation, usually is done during each epoch, and validation actually sees, the model and you iterate on it. So just to be sure, the results that you're presenting, are they on data that has never seen the model before, right? And then you don't fine tune after that. Okay.
So since we only had like 2 sets, we were actually just calling the test set the validation set. So yeah, sorry about that confusion. Yeah. So
any questions from others on the call?
Yeah, this is Karthik. I have one question. So on what basis you guys set the final goal as 70 to 75%? As other two data sets were showing 90+, correct? So you were all 3, or you consulted expert and came up with the final goal, or how it works?
Milind, do you want to answer?
Yes. So actually, for this, what we did is that because the other data sets contain so many more features for each patient, like our data set only contains 11 very simple features, such as like age, height, weight. There's no genetic markers or any other things that could help the model. And thus, so while other like data sets, like researchers may be able to achieve higher accuracies, the thing is that we hoped that like our model could be useful in places where like it may not be possible for people to test all these different genetic markers and things for cardiovascular disease. And so we wanted a model to be able to use only very simple features where you can find it anywhere, such as age, height, and weight. And so in order to determine our project goal, what we did is we had an expert manually classify just like a random sample of 100 patients. So they randomly chose 100 different patients. And then we looked at their accuracy. Their accuracy was around 77% and 0.77 F1 score. And then we regard it as a proxy for Bayes accuracy. So Bayes accuracy is like the highest theoretical accuracy you can achieve given the data that you are given. And so we made a binary accuracy and F1 score a little bit lower than the Bayes accuracy or the highest accuracy. And so that's how we came to the thinking of around 70 to 75%, or an F1 score of around 0.7 to 0.75. Does that answer your question?
Yeah. One more final question. So I see like a lot of reference to rural areas in third world countries. So can you tell us whether you used the data set with rural area and a third world country data set, or?
So this data set was not collected in a third world country. But we were hoping that because it uses very simple features that we would be able to apply it to third world countries and rural areas.
Okay. Thank you.
I do have a question. This is Govind. So the as you just mentioned, the data set is not typically of a rural country. Definitely, it would help to know the differences in the BMI and all those other parameters as they vary from what is a rural setting to what is the urban setting. You probably know that in the rural area, people have they tend to have different kind of work ethics than urban people. They are not necessarily bound to a chair. So in some sense, I mean, I think a justification of saying that these 11 features would apply to a third world country, to me, I think we need more validation of that assumption. But other than that, the project is excellent. I have no doubts about that part. I'm just saying in terms of validation of features. The other thing I would like to know is typically if you were to take this project and make it better, you did identify the application, different applications around it. But if you were to take this project and redo it, or if you wanted to go, if you had to take it to the next step, what exactly are the kinds of things that you might be doing?
I think also one of we had like that listed in the slide, but also I think one more thing that we could do that would really help. So I think if we could find more data and like collect from more diverse places, which is we tried to do that, but I think if we continued on that path and tried to find even more data sets, because I feel like our network could have done better if given more data and if given also like varying different types of data. So like using transfer learning or if we didn't get the data, to get like probably from different neural networks that have already been trained in bigger data sets. If we could use some of that and use transfer learning to help with the task that we have, I think that would improve our accuracy. And I also think that if we used like a bigger model, maybe with more layers, and if we got more data, I think like both of those would combine. And since we have more data and a bigger network, that would really help us to achieve a higher accuracy. Because like in the graph that we had showed, deep learning models tend to perform a lot better when given more data. And I just feel like our network wasn't given enough data to perform as well as it could.
I have another follow-on question actually. So I think I agree with your statement that essentially, deep neural network definitely benefits a lot from more data. That's kind of well-known fact. So the thing I was trying to figure out, which I could not get an answer to, is that were you able to characterize the dropout regularization in terms of its ability? How did it actually help? Whether it helped in terms of improving the accuracy? Regularization has two objectives, right? One has to do with the optimization issue, and I was trying to figure out if there's some relationship you found, which you might have documented, and that could be a very interesting. Actually, it could be a good paper to publish if you people can repeat this experiment and look at how regularization actually, with a small data set, how it is actually helping you. I think that's academically, it's a very interesting problem. That's pretty much more of a statement rather than, any question as such.
Yeah, thank you so much for that input. Yeah, so we'll see.
Good
we'll
motivation.
see if we can find that out.
Awesome. Hey guys, we're really up at time here, but really good questions here, and I encourage those of the folks here who actually commented and provided good suggestion, Karthik, yourself, others. Please to reach out and have those conversations offline, and continue mentoring the students here if they do seem so inclined. We would like to wrap up our Q&A session over here at this point, just considering the time and everything. Mike, back to you.
Okay, yes, we are at 8:40, so perfect timing. Really great presentations by everyone. It's a fairly new thing for us to feature this, and so I think we've learned a lot about the benefits of having this young talent. So again, thank you, everybody. And if there's nothing else, we call this webinar to adjourn. Bye-bye.
Bye-bye.